passing through our solar system actually be older than the sun itself? If you've been following my previous videos on 3i Atlas, we've already answered two important questions. First, artificial intelligence and machine learning identified it as one of the most unusual cometary objects ever observed. Then, using NASA's JPL Horizons data, we confirmed it was an interstellar visitor passing through our solar system. But now, the James Webb Telescope may have answered an even bigger question. Where did it come from? Hi everyone, I'm Dr. Amanda Fetch, aka Dr. Amanda Analytics, and on my YouTube channel we explore artificial intelligence, machine learning, space situational awareness, and the data behind today's biggest discoveries. Today we're bringing together three different scientific approaches to tell the story of one extraordinary object. So let's dig in. Before we look at the newest discovery, let's briefly recap what we already knew. In my first video referencing 3i Atlas, I analyzed thousands of comet orbits using a machine learning clustering algorithm called dbScan. Rather than searching specifically for interstellar objects, the algorithm grouped together comets with similar orbital characteristics and naturally highlighted out the anomalies. Almost every comet clustered around an eccentricity value of about 1, exactly what we'd expect for objects gravitationally bound to the sun. But two objects stood immediately out from this analysis: Borisov and 3i Atlas. Machine learning didn't identify what the objects were, but it did identify that they were fundamentally different from the rest of the comet population. And so that was our first clue that something extraordinary was hiding in the data. Now in my second video, which again you can find both of these videos on my YouTube channel, I turned to NASA's JPL Horizons system to better understand the comet's trajectory. Horizons provides astronomers with precise orbital information for objects throughout our solar system. One number immediately stood out: the eccentricity value. 3i Atlas has an eccentricity of approximately 6.14. For comparison, any orbit with an eccentricity greater than 1 is hyperbolic, meaning the object is not gravitationally bound to the sun. In other words, it didn't originate here. It entered our solar system from interstellar space and is simply passing through. The Horizons data also allowed us to track its motion over time. And so we could see its distance from the sun steadily increasing, while its outward radial velocity continued climbing. And so everything about the orbital data confirmed the same conclusion, in which 3i Atlas was leaving our solar system. And it's not coming back. Up to this point, however, everything we knew came from orbital dynamics. The data told us where the comet was going, but it couldn't tell us where the comet originally formed. That's where the James Webb Telescope starts to change the story. So earlier this week, NASA published a new article summarizing Webb's observations of 3i Atlas, based on a newly published Nature study. Now those observations, if you dig in, provide the strongest chemical evidence yet for where this interstellar visitor may have formed. According to NASA, as 3i Atlas moved away from the sun after its closest approach, sunlight warmed ancient ice trapped inside the comet. That ice sublimated into gas, creating a bright coma around the nucleus. Using its near-infrared spectrograph, or NIRSpec, Webb analyzed that gas in a remarkable amount of detail. And so instead of really just taking another image of this comet, Webb measured really its chemical fingerprint, which is fascinating. Specifically, researchers mapped water, carbon dioxide, and carbon monoxide through the comet's coma and analyzed the isotopes contained within those molecules. Now, the biggest surprise they found came from two isotope measurements. First, Webb found that 3i Atlas contains approximately 30 times more deuterium, probably butcher this, or heavy hydrogen, than astronomers typically observe in comets originating within our own solar system. Now, second, the comet isotope ratios were significantly different from those measured in solar system comets, showing much lower levels of carbon-13 relative to carbon-12. Now, these numbers act like chemical fingerprints, as I mentioned, that preserve information about the environment where the comet originally formed. So scientists can use isotope ratios to reconstruct conditions that existed billions of years ago, even though those environments can no longer be directly observed. Now, through this chart I recreated key measurements from the study to better visualize for us the differences. Now, if we look at this compared to typical solar system comets, 3i Atlas shows dramatically elevated heavy hydrogen and distinctly different carbon isotope ratios. Together, these measurements suggest that the comet formed in an environment that was significantly colder than the region where our own solar system formed. Now, to better visualize what that means, I created the timeline. Based on the Webb observations described in NASA's article, the researchers estimate the 3i Atlas may have formed between 10 and 12 billion years ago, during a period astronomers call cosmic noon, when star formation throughout the galaxy was occurring at a much higher rate than it is today. Now notice where 3i Atlas falls in the timeline. Our sun didn't form until approximately 4.6 billion years ago. Now if these estimates are correct, this comet may have already existed for billions of years before our own solar system was born. Now when we think about that, in my opinion, that's one of the most fascinating aspects of this discovery. It means we're studying material that may have formed long before our own sun even existed. But what I find even more interesting than that is how each scientific approach that I went through in this video answered a completely different question. So we used machine learning, which identified the 3i Atlas was an orbital anomaly. We looked into NASA's JPL Horizons data, confirming that it was an interstellar visitor following a hyperbolic escape trajectory. Now we have the James Webb Telescope, which provided chemical evidence that allows scientists to infer the type of environment where it likely formed billions of years ago. Now, none of these approaches alone could answer that full question for us. But if we start piecing them together, again, we have machine learning, orbital mechanics, spectroscopy. We build one of the most complete pictures that we've ever had of an interstellar visitor. Now that's what makes these discoveries really exciting. So they remind us that no single technique has all the answers. So it's something to think about as you're working through some of these analysis on your own and, through different processes. Now, understanding the universe often requires combining multiple analytic approaches, each contributing a different piece of the puzzle. Now, with that being said, I'd love to hear what you think about all of this. As more interstellar visitors pass through our solar system, do you think combining artificial intelligence, orbital mechanics, and spectroscopy, tongue twister, will fundamentally change how we study objects from other star systems? Let me know your thoughts in the comments. Now, if you enjoyed this video and my continuation of the 3i Atlas series, please consider giving this video a like and subscribing for more content on artificial intelligence, space, and emerging technologies. With that being said, thank you so much for tuning in. Take care, and I hope I'll see you in the next video.